Singular value decomposition, abbreviated SVD, is a nifty concept present in processes like formulating Netflix recommendations, constructing facial recognition algorithms, and working with data compression. We'll be delving into the application of SVD in the context of image compression to reduce image size while visibly maintaining the image's details intact.
This process is very useful for compressing images that do not require an extensive level of visual detail, allowing the storer of the data to get away with storing an image that looks the same, but requires less saving data stored than the original. The image is now a smaller size while still appearing the same as the original, thus saving space.
The underlying concept behind SVD takes a matrix, let's call it M, and decomposes it into constituent submatrices, U, sigma, and V transpose.
In order to find U, we must first find out the matrix of M transpose. For all intents and purposes, we'll call M transpose A for the following equation.
Next, we need to find the eigenvalues of A. To do so, we will take the determinant of A minus lambda I and set it equal to 0. After plugging in the values for the matrices and solving for the quadratic equation, we get the eigenvalues to be 25 and 1.
Then we'll take the eigenvectors using our lambda values from 1 and 25, and we come up with 1, 1, and negative 1, 1.
To finish up, we'll normalize the vector, giving it a magnitude of 1 using the Pythagorean theorem. This resulting vector must be orthogonal, and since it is a symmetric matrix, it is already orthogonalized. For non-orthonormal matrices, apply the Gram-Schmidt to orthogonalize them.
Next, we need to find out what V transpose is. To do this, we'll take the eigenvalues of M transpose M, and they should be the same as MM transpose, which is 25 and 1.
Next come the eigenvectors, using our lambda values of 1 and 25. Coincidentally, they are the same eigenvectors of those of A, but this will not always be the general case.
To find V, we need to normalize the vectors, giving them magnitude of 1 using the Pythagorean theorem. The resulting vectors must be orthonormals, and since they are a symmetric matrix, they are already orthogonalized. For non-orthogonal matrices, apply the Gram-Schmidt process to orthogonalize them.
Then, rearrange the columns and rows of matrix V to find V transpose, the submatrix of M we are looking for.
Now that we have matrices U and V transposed, all we need is sigma. In order to find it, we place the square roots of the eigenvalues in descending order diagonally.
And there we have it. We have successfully decomposed our matrix into rotational matrix U, scaling matrix sigma, and our other rotational matrix V transpose.
In the context of image compression, we can rewrite our matrix M as a linear combination of the columns and rows of U and V transpose and our sigma values using the sigma values in decreasing order, as the highest values are more important in the decomposition. In each term of M, we have a n by 1 column matrix U, a scalar value sigma, and a 1 by m matrix V transposed. The total number of bytes held in this term thus will be n plus m plus 1 bytes. We can then repeat this for as many k terms as desired, with each term helping reconstruct the original image matrix, but progressively improving the image quality less and less as their sigma values decrease.
Let's now take a look at this image. It's more sizable than the matrix M we just worked with, but it uses the same concept. The figure title shows the k values used in the decomposition in real time. At some point, we can stop the SVD before the full image matrix is reconstructed because the human eye can no longer see the detail of the image improve as our k term increases. Therefore, our final compressed image size will be n plus m plus 1 multiplied by whatever number of k turns used before stopping the SVD.
In our particular case, our compressed image size is 213,500 bytes, as opposed to the original's 1,049,088 bytes. Comparing both images, it's near impossible to tell the difference.